Hi everyone, this is my ANSYS Know House share. I'll be telling you a few little points to remember first. There are three kinds of elements we'll be using in lab. They are link, beam, and solid. Link we'll be using if the question is about bars only. Beam can be used with both bar and beam. And solid elements are used with areas and 3D objects. So that's the first rule. Second rule is static. In static analysis, you will be only putting the values of Young's modulus and Poisson's ratio. Whereas in modal and harmonic analysis, you will also include density. So that's another point to remember. Then loads. In static analysis, you will be giving loads if the question has it. And in harmonic analysis also, you will have to give loads. Whereas in modal analysis, you will not be giving loads because everything's done in free vibration, and it's just testing like how the material behaves for every mode shape. So let's go to the questions we solved in lab. This was the first one. A bar having square cross section with edge length of 30 mm and length of 1000 mm is subjected to a tensile load of 10,000 newtons by considering the Young's modulus as 210 E9 pascals. Determine the deformation at 0.3, 0.5, 0.7 meters. The stresses there and the reaction forces also. Open ANSYS. You know the problem now, so it's structural. Create an element type. Let's take beam because it can work with both bar and beams. Go to material properties, material models, structural, linear, elastic, isotropic. 210 E9 is Young's modulus and zero point 0.3 the Poisson's ratio. Then go to sections, beam, common sections. It was a square cross section for 30 mm on each side, so it's 0.03 meters. Let's give OK. Modeling, create key points, inactive CS, apply for 1 meter, 1000 mm, no? So 1 meter. Now create a line that connects these 2 points. You need to mesh this now. Let's mesh it in the way that we can select those 0 0.3, 0 0.5 and 0.7 places on this line. So go to meshing. Uh, you can also use the mesh tool. Go to line set, click on this line, give element divisions as 10 because we want 10 elements. Okay, take the mesh tool again, mesh this line, close that mesh tool, it keeps appearing. Now meshing is over. Go to loads, analysis type is static, it's already there. Now go to define loads. You need to fix the left end on key points. All DOF is 0, and on the other side we need to give a load of 10,000 newtons. So go on to that key point, give Fx. This is along the x-axis, so Fx 10,000. Okay. Now go to solution, solve current ls. You'll get it solved. What do we need to find out is the deformation, stresses, and reaction forces. So go to general post processing. So we wanted to find the deformation, no, at 0.3, 0.5, 0.7. So go here, click on nodal solutions. That gives you the displacement at various points. So this list gives you the displacement at all these nodes. We made 10 elements, so 11 nodes. You want it at 3, 5 and 7 here, so just copy those values. And then second question was to find the stresses and reaction forces. Go to element solution for stresses. Here you will find stress. Since we applied the load in the x component direction, click on x. You'll find that the stresses are the same throughout the body because it's uniform. Then you need to find the reaction forces. Go to reaction solution on fx direction, click OK. That's minus 10,000. So since it's uniform, you have the same value throughout. If you want to look at the 3D figure, just go to plot, deform shape, click on this plot controls and switch on uh, from size and shape. Click on 3D. If you want to see the nodal solution, this is displacements along every part of it, like at each element. So that's all with question 1. That's what I have put in my results. So they have asked another question. For the above tutorial, compute the theoretical solution and find the displacement and stresses. To find the theoretical solution, we know we can split the given bar into any number of elements. For accuracy, I mean, it converges with 4 elements itself since it's linear throughout. So we know this area, cross-sectional area, length, load, Young's modulus, everything. Simply substitute in this formula. We know AE by L 1 minus 1 minus 1 1. Displacements U1 U2 for loads minus P1 and P. This P gets interpolated throughout when you do for all 4 elements, and when you see the final assembled matrix, you will have all these displacements up to 5 and minus P and plus P here for the loads. On computing this, you will get values for each of these displacements. So that satisfies the answer for this question, and you can just compare those values and write something. Then let me just pass on to the ANSYS questions. Create 3 cross sections of 20, 30 and 50 mm. Calculate the displacement and axial stresses. We just saw how to find the displacement and axial stresses, but how do we create these cross sections? Let me show you. Start clear, go to preferences, it's structural, preprocessor, element type, add beam 2 noded, close. Go to material properties, material models, structural, linear, elastic, isotropic 210E9 and 0.3 for steel. Since in this question the all 3 cross sections are of the same material, steel, so we are not going to require many material models. So this one's fine actually. Just one material model and you close this. Now go to sections. Here in sections you will be creating so many, I mean 3 different cross sections. For ID number 1, create a cross section 0.05, 0.05, since it's 50 mm square cross section. Give apply, change the ID to 2, then give cross section as 0.03 and 0.03 for 30 mm square cross section. Then click on apply, give the third set 0.02, 0.02, and there you're done with the 3 cross sections. Now you've created 3 cross sections. Go to modeling, create key points, an active CS, give 0, give 1, give 2, give 3. So you have created all these 3 points. Now while drawing lines, go to straight line. You have created 3 lines. Now go to meshing, mesh attributes, pick lines, this thing, apply. This is material number 1, beam element 1, element section 1, oh, apply. Now click on the second line, give apply, change this. The material is the same, so is 1, but the beam type is 2, right? So click on 2 in the cross section, I mean element section is 2, that gives you 30 mm square cross section. Now click on apply. Now click on the third line, apply, change this element section to 3, click OK. So you have 3 different element cross sections for these lines. Now you need to mesh them, right? Mesh lines, all these lines, they are meshed. Now go to loads, You're doing a static analysis, isn't it? There is nothing called modal here. So you're doing static analysis. Analysis is static. Just check that. Now define loads. Go to structural displacement. Click on the left side. Key points. Click on the left side. All DOF 0. Now change the force on that side. Do we have to give a force? Let's check anyway. Create three cross sections. Yeah, I think you have to give a load. They are considering the same question but with three different cross sections. So let's give the same load on that key point. Otherwise you won't get anything. No. F axis, I mean X axis, give 10,000 newtons. Now we are done with loads. Go to solution. Go to solve current LS. You'll get it solved. Then go to general processing. What should we find out? We should find out the displacement and stresses, right? And the reaction also. So all three, just like we did for the first one. Go to plot results, deformed shape. You get the deformed shape. Then you go to what should we find out? First, we should find out the displacement. So here it is. You'll get the displacement for every element. If you want to list it, just go here to list results, nodal solution, displacement vector sum. You will get it for every node. You can copy that and paste in your results. Then you go to element solution for stresses, X component. You get it for every section in every node. Okay, just copy those values. They're actually the same for every section, but they are not same among every nodes in each section. See, for uh, for the first section, it's 40 into 10 power 7 throughout. Then it changes to 0.11. Then it changes to 0.25 10 power 8. So copy those values. Then go to reaction solution. F-axis is 10 minus 10,000 reaction everywhere because there's only one load. Okay. So that's how you do this. If you want to see it in 3D, go to style, size and shape. Click this thing on and click on this space. You can see in 3D. Okay. So the next question. A composite bar consists of steel and copper having constant square cross section area with edge length 50 mm, square cross section with 0.05 meters. Okay, and then the length is 1 meter. For the same bullshit, displacement, axial stress, you know how to do all this, but the only difference is we have two sections here. Just like we did here, you have to give a material model for the first section and you have to give a different material model like copper's values here for the second section. That you'll be doing here in the preprocessor. Material properties, material models. You just add a new model here as model 2 and select its properties. For copper it's 1.17 E9 and Poisson's ratio is 0.3. Once you do this, while you are meshing, no, go to this mesh attributes, pick the lines. When you click on this line and give OK, here it will be changing to 2, material model 2. That's all. Everything else is the same. So that's all with question 1. I'll just take a small break and come up with the next set of, exercises. This was the answer for the ones we did just now. Let me go to view page display 2 page. So this is the theoretical calculation, displacements, reaction forces, stresses, and for the different sections we have the same theoretical, some screenshots, displacements. So that's how you write the result and just throw it on his face. Bye bye for now.